So the question is, in this Markov chain that we're talking about, either called the gambler's ruin problem or the drunkard's walk problem, there is only a reward for these special states at the end. So if you get to this end, we stop playing the game, you get 0 life points and you're done. If you get to this end, you get 1 life point and you're done. And I said that in a Markov chain with rewards, there are rewards everywhere. So actually, you could also say that there's 0 rewards at every intermediate step, and those aren't sort of part of the game. So the special case of having no rewards for most of it and only having some special states that give you a reward is a special example of the more general thing where you can have rewards everywhere. And we're going to do some more complicated examples with that first, but this is like the simplest first example where only these special last states have rewards. So this is special. Only, I'm going to call them the terminal states have rewards, but that doesn't necessarily have to be the case. Does that answer the question, Rob?
Yeah, that's perfect. Thanks.
Yeah. Any other questions? Someone in the chat wrote, how do you, if you miss a lecture? So they're automatically recorded on Zoom. So if you click on Zoom, you should be able to go to like cloud recordings and watch them there. Okay. So yeah, again, feel free to anytime put your hand up or type something in the chat and I'll try to keep an eye on that. Let's see what people thought about this problem, which we call it. Let's open that up. What name of the problem do you prefer? Oh, okay. There was an early lead for Gambler's Ruin, but Drunkard's Walk took the very slight lead at the last second. So in this problem, you can think of your state, right? You have all these states, which I've drawn in blue here. You can think of your state as the amount of money in your bank account. So you have $0. And then after betting some money, you can either get $0 plus $1 or $0 minus $1. And then in that interpretation, this is the gambler's ruin problem. The question is, do you get ruined? When you get to $0, you're broke and you're ruined. Do you get ruined before you get to your target? And I guess when you reach your target, you're very happy. In the super pessimistic version of this problem, the gambler has a life-saving operation that costs n target dollars and will die unless they get n target dollars. That's why n target dollars is worth 1 life point. And anything else, getting down to 0, is 0 life points. But you guys want to call it the Drunkard's Walk. And in the Drunkard's Walk interpretation, same exact problem. The interpretation is that you are a person and you are at some distance away from your house and you are at some distance away from a cliff. I guess a cliff looks like this. And there's like spikes at the bottom. And so this person is a little bit drunk, so they're moving back and forth randomly. So they start at position x0, they can go to x0 plus 1 or x0 minus 1, and they move back and forth and they sort of like wander back and forth this way and that way. And the question is, do they get home and go to sleep first, or do they fall off the cliff first? And they'll keep walking around until they do that. Either way, it's the same problem. And we want to know, question, this is the important question. Given the starting position, what is the expected value of the reward given x0? So you're told where you start, and you don't get to find out the reward until a long time later, right? It takes a long time until you fall off the cliff or reach your house. And you want to know, what is that expected reward given your original position? This function is called the value function sometimes. So this is called the value function. So the value function v of x0 is defined to be this thing. In this case, the reward given, I'm gonna write it like this: x0 equals x0. Let's just write it with an x, so things are clear. So x is one of the states, and for every state in space, you can think of starting at that state, and what is the long-term reward given that the Markov chain, which I'm drawing with a capital X, capital because it's a random variable, it starts at lowercase x and it goes until whatever happens. So finding the long-term value of the reward, that's what we're doing. And this is extremely close to the long-term goal of the course. So the long-term goal of the course is this reinforcement learning thing. We want to learn something about some problem. Here we want to learn the value function. Later in the course, later, we are going to learn the value. That's what we're doing today, just the value. But later on, we're going to do the value and the optimal choice. So in this gambler situation, there is no choice. The gambler is just going back and forth. Or I'm going to stick with the drunk guy. The drunk guy has no choices to make. He's just going back and forth, and we just want to know the value. Later on in the course, we're going to define the exact same kind of situation with choices. So the drunk guy maybe can make a choice if he wants to step forward or backward or something. And the big question of the course is, how do you estimate not just the value, but also the optimal choice? And before you understand that one, you really got to understand just the value first. That's what we're doing today. Okay, so we're trying to learn the long-term value. Last time I briefly teased the Monte Carlo method. This is the first method we're going to use. The method one to solve this problem. Method one is the Monte Carlo method. And Monte Carlo is a big casino in Europe. And the Monte Carlo method means run many simulations. That's the idea. Simulations. So let's go over how this one works. And I think I briefly teased it last time, but let's just do it again. Okay, so, and I'm going to try to go slowly here with the Google Colab so you guys can see what's going on. This course really has like two orthogonal components. One is understanding the math, and one is understanding the programming. And the programming shouldn't be too hard if you've taken a course before, but feel free to stop me anytime if there's something that's unclear. Let me know, and we can have more or less like tutorials about how to do the programming. We can do some outside of class time too, if people are interested. But so in Google Colab, it's like a Google Docs file, but for programming, not just a Word document. And when you hit the play button, the code will run on Google's computers. The first block is always importing a bunch of packages that we'll use. And the main ones we want to use are ones that let us use arrays. So Python on its own doesn't have arrays, it has lists. And lists are good because they can be any length, but they are slow. So we want to do arrays, which are like a fixed size, but are super duper fast. So that's what we're doing here. We're importing some of these things. Here is the description of the drunkard's walk problem that we're doing. And you can think of it as a Markov chain by saying you move forward from state X to state X plus 1 with probability P, from state X to state X minus 1 with probability 1 minus P. That's moving forward and backwards. And there are these two special states, state 0 and state end target. And if you ever get to those states, you're stuck forever. So those are sort of terminal states, or sometimes they're called absorbing states. If you get to these special two states, you're finished. And we just want to know what is the expected value of the reward starting from some point X. Because the reward is always 1 and 0 in this special problem, you can also say that as the probability to reach the target, right? If you get 1 point when you reach something and 0 points if you don't reach it, then the expected number of points you get is the same as the probability that you reached the target. Okay, and we're going to do the Monte Carlo method. Here is the simplest possible Monte Carlo method. We're inputting 3 things about the problem. The end target, that's where we want to get to. X0, where we're starting. And the other thing is n samples. And so in a Monte Carlo method, you run many simulations, I'll say, with independent. You want them to be independent samples. Independent samples. And you use the independent samples to estimate the value you want. Use the independent samples to estimate the value you are looking for. Okay, so here's how we're going to do it. And I think it's easiest if we just look at the code. I'm just going to run n sample independent samples. And what I'm going to do is I'm just going to keep track of the total reward we get over n samples. And then at the very end, I'm going to take the total reward and divide it by the number of samples, and that'll be an estimate for the expected value. So this is like the experimental average. And we're crossing our fingers that it's close to this expected value that we're looking for. So there's a for loop. I loop over the number of samples. So this is sort of doing, each entry of the for loop is doing its own independent sample. I have this random variable capital X, and capital X represents the position of the Markov chain. So it starts at x0, the original location, and then there's a while loop because the Markov chain just moves around until it reaches one of these two terminal states. So this while loop, while x bigger than 0 and x is less than n target, that is exactly corresponding to what is going on before you reach one of these two terminal states. And before you reach one of those two terminal states, you're just moving around randomly, and that is exactly what the code does. So the code takes your position, capital X, and it's adding on either +1 or -1. How do I get a +1 or a -1? I use this rand_int function that gives me a 0 or a 1. If you get a 0 or a 1, I want it to be a +1 or a -1. So I take 2 times 0 or 1 -1. This converts, maybe I should write a comment here. 2 times, how should we say it? 2 times 0, 1, -1. Random variable is a -1, 1 random variable.
Did you just pass in -1 and 1 into the rand_int function?
If you pass in -1 and 1, then it will give you either -1, 0, or 1.
Oh, okay.
Yeah, that's a great question. So there's only 2 possible outcomes, so I better use a random function that has 2 possible outcomes. And you'll notice actually that I did something simplifying already, just for the sake of convenience. In the general problem, there's a p and a q. So there's the probability to move forward, that's p, and the probability to move back is 1 minus p. And in my simple simulations today, we're gonna assume p equals 1/2. Of course, it wouldn't be very hard to change it up to make a different value, but p equals 1/2 is a nice number. You're equally likely to move forward or backwards. In general, you can do it for any number. So maybe I should put that here. We are assuming that p equals 1/2 here, equally likely to move back or forward. Yeah, so in the chat, someone said you could also do random choice of a -1 and 1. That's also possible. You have to be careful with random choice sometimes, because sometimes it will have a setting of with replacement or without replacement. And if you use the wrong one, then it'll like alternate between -1 and 1 in a way that you don't want. So random choice can work as well, as long as you're careful with it. Okay, so while we are not at this terminal state, we just are moving backwards and forwards. And eventually, hopefully, we reach either x equals 0 or x equals n target. And when we reach either x equals 0 or x equals n target, then we are done. We stop the simulation, and we take our reward and we walk away. Maybe this is a good time to introduce some terminology. So different branches of mathematics have different terminologies. I've been saying simulation. I think that's a good way to say it. In the reinforcement learning community, they call simulations episodes. So one episode, aka one simulation, is run it until you reach a terminal state. So like one run of the thing. And okay, again, you got to be careful when people say this. They sometimes mean different things, but that is a word people will use. Okay. So we run it until we reach one end or the other, either 0 or n target. When that happens, we exit the while loop. So maybe I should add some comments here. So while loop runs until the location reaches either x equals 0 or x equals n target. I can say what this was. This is initialize the position. And remember, the function depends on x0. So we're calculating for a given x0, we're calculating what is the expected reward. And in general, we want to know what this is, but this function only does it for one value of x0. Okay, finally, after we exit this loop, we add 1 to our total rewards if we are at the right terminal state. So if at the terminal state x equals n target, that means the drunkard made it home and didn't fall off the cliff. Then add 1 plus 1 to total rewards. Okay. So we run this. Now we go through the for loop, n sample times. It's doing all the samples are independent because when you do random.randint, it makes independent coin flips. So what happens in one episode, it does not affect anything in the other episode. We run it n sample times, and at the end, we return the total rewards divided by the n samples. This is kind of like return the experimental average. And we hope that it is close to the real average. That's what we actually want. Okay. So I press play. That means that it ran this, and now it knows what this function is. And now hopefully, if I run it, it'll figure it out, and it'll output something. So here I'm running it with 10, 5, and 100. If you read what that means, n target is 10, x0 is 5, and I'm doing 100 samples. So, you have 10 states, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And remember, 0 is dead and 10 is go to sleep. I don't know, how do you draw dead? Like this. So the drunkard starts here at 5, and we want to know, does he make it home first, or does he fall off the cliff and die first? And when we run it, what do we get? We got the number 0.46. So 0.46, it has the interpretation of being his expected reward. The expected reward given x0 equals 5. We think it's approximately 0.46. And you can, because the reward is either +1 or 0, you can also interpret it in this particular case as this is the probability to get home safely. Given x0 equals 5, it's approximately 0.46. Okay, so that's the very first method, the Monte Carlo method. There's a couple of questions in the chat. Yeah, so someone in the chat, I think, asked, how do we choose the x0? And ultimately, we want to know for all possible x0s. The function just takes one and calculates it for that x0. You could run it, I guess, 9 times to figure out the other values. Any other questions or comments about the Monte Carlo method? This is our first kind of solution method, the Monte Carlo method.
One quick question. I mean, I sort of asked this after class one time, but
yeah,
when you're relying on randomness coming from the computer like this, you don't just be a little bit worried that, like, if you get an expected answer that it's actually right, or
okay, so you're worried. I think last time you asked me about this, you were worried about this randint function. Like, is it actually random? Yeah. So that part, I think you should not worry about. So it is true that the random.randint function is not actually like 100% random. For what we're using it for, it's totally fine. So it should, on average, put about half the time zeros and half the time ones. For what we're using it for, 100% A+, like, you should not hesitate to use these functions. They work perfectly well for this. This is what they're designed for. If I was a bank and I was designing, something to keep out hackers using this function, then I would worry. So if like a human is on the other end who can like try to exploit this, then I would worry, and it's not truly random. But for this purposes of like running simulations, these are perfectly good, and you don't need to worry about the randint function not actually being random.
So like it effectively gives you like a good spread of points, like a good distribution.
Yes. Yeah. Right.
Okay.
Yeah. And again, it's a complicated problem. Like if we had to write the randint function ourselves, there are lots of ways we could like fall into a trap and like make something that doesn't work. But fortunately, the guys at the at the Python University have already done it for us, and this random function is pretty good. So you don't have to worry about that.
Okay. Thanks.
Yeah. No, that's a really great point. And I think this is one of the things. The Monte Carlo algorithm relies on having like proper randomization of the thing you think you're simulating. So we think we're simulating this random walk. If our randint function didn't work the way we thought, then of course we'd be simulating something else. We'd get the wrong answer. Yeah. Anybody else? Okay, so I want you guys to answer this question now that we've done the Monte Carlo algorithm. The next question on Mathematize is tell me a pro and a con of this algorithm. And of course, there's no ultimate right or wrong answer. There are many advantages and disadvantages of this method. But basically, this is the first thing that pops into everybody's head. If you ever go on to like Reddit or something and find a problem involving probability, this is the only method people use to solve them. Sometimes it's very good. Sometimes it's not so good. Why don't you guys think about it for a sec and tell me a pro and a con based on what we just saw. Okay, so I'm going to copy the link into the chat. The code is also in my name on Zoom. So if you ever need the link, you can go to Mathematize. It'll ask you for the 4-letter code, and it's in my Zoom name. Today it's a PSOF. Okay, yeah, Rob sent it. Thanks, Rob. Okay, yeah. So there is I think these are supposed to be like shorter words. So if you run into a character limit, try to condense your idea down. It's like a ultimate Twitter version of pros and cons. Yeah. So don't worry about it. I'll interpret. I guess you could also, if you have something longer, feel free to. We'll have a sort of little mini discussion right now. So feel free to put it in the chat, and we'll just sort of use this as a guideline anyway. So I have 6 responses. There's 22 people. Let me give you guys like 1 more minute to finish up your ideas. So let's get this timer going. Okay, time's up. Let's see what you guys said. An advantage is good approximation. Computer does the tedious work. This is true. Like, you don't actually have to do any hand math to do the Monte Carlo. It's relatively easy and simple to code. I definitely like that. Let's write this one down. So, pros and cons. Monte Carlo MC pros, MC cons, and one thing for sure, it is easy. So all the stuff we did last week with matrices and understanding Markov chains, you don't need any of that to do the Monte Carlo method. And this is why another reason it's super popular for sort of random problems you see on the internet. You don't really need to know a lot of math. You just kind of program it into a computer and you run it. And the computer does all the hard work. So maybe minimal thinking. Okay. All right. Easy. Simplicity. Most people look for easy. Okay, great. Large number of samples. I guess, is that a good thing or a bad thing? So whoever wrote large number of samples, do you want to tell me why? The character limit got you. Why is large number of samples a good thing? It's okay if you don't want to let me know. I'm trying to think of how large number of samples could be a good thing. I guess the thing is, on modern computers, you can easily run a large number of samples. So, if you were doing this in the 80s, that would have been more difficult. But now everything's quite simple. Okay, let's look at cons. A disadvantage of the algorithm is very slow when coded this way. So I believe it can be slow. When coded this way. Does someone want to tell me what is slow about the way I coded it? What's the other way? Was there a different way to do it?
I put slow and coded this way because you're using two loops. You're using the for loop, which takes one iteration at a time and then goes through the entire section. You can do it in parallel. I'm not sure how to do it this second, but if you do it in parallel, it could be a heck of a lot faster. You could do it all at once.
Yeah. Okay. So it can be slow. I totally agree with that. And this way, 100% right. It can be slow when you do it this way. I believe is a 100% accurate statement. And this way means not parallel. So the way I coded it is not in parallel. The computer is only ever simulating one sample at a time. And you can see that because there is a for loop. Let's go to the code. So I have these two loops. And what it means is that because I'm doing loops, one sample cannot start running. Nothing can happen in sample number 2 until sample number 1 is done. So I'm first I do all of sample 1. I wait for it to finish. And then I start sample number 2. I wait for that to finish. Then I do sample number 3 and so on. And so I'm sort of doing the sequence of events. I'm doing sample number 1, then sample number 2, and so on. And this is very slow because to do sample number 100, you have to wait for all the other ones. And we're going to see there is a faster way to do it where you sort of do all the samples at once. And this really takes advantage of modern computers are good at doing more than one thing at a time. So your computer can do a lot more than just add up like one number in one operation. It can do like a whole bunch of numbers. And you'll see that there's much better ways to do this. So we are going to get to this, and you can do it in a better way. That's coming up. So very good. Yeah, the way I did it, super slow. By the way, you'll never ever see the fast way to do these things on the internet in the wild because it's a little harder. So you can sacrifice some easy for some speed by doing them in parallel. We're going to see that soon. So I guess this is called in serial when they're not parallel. We're going to get to that. Great comment. Okay, let's go back. Other pros and cons. Different answers. So when you run it, if you run it again, you get a different answer. Like we got 0.46. If we run it again, now we got 0.48. So what is 0.53? What is the actual answer? The answer you get is not the real answer. It is a random answer. Answer is random. Right? It depends on how the coin flips came out. You don't get the real answer. And this is related to maybe even more specifically. Let's see. Yeah, not exact, not exact. So accuracy. So really, the answer is random. It has some error. And like the fundamental question should be in your mind, how big is the error? Is the error? And this is like when you're doing stuff with computers, you should always keep this in mind. Even the best computer program, because the computer only stores things to so many digits, it won't be the exact answer. So like in paper math, if you do 1/2 plus 1/3, the real answer is oh boy, I better get it right, 5/6. Like that's 100% right. If you do 1/2 plus 1/3 on the computer, you won't actually get exactly 5/6. You'll get something like with decimals, and it'll have so many decimals before it will stop. So there's always some error on a computer, but normally that error is like 10 to the minus 8 or something, like extremely small. In the way we're doing it, there is a much bigger error, and like you really need to keep in mind how big is the error. Like how long would it take us to make sure that the error coming from this randomness is less than, say, the error from the computer already. So like this fundamental question of how big is the error is really important, and most people like don't think about it. I think anytime you're doing a Monte Carlo, this should be the only thing in your brain. How big is the error? You really want to know how big is the error. So the way I've written it, not only is there an error, like the answer is random, but I don't even know how big is the error. So the way I've written it, not even sure how to estimate. How big the error is. So that's one thing. So 2 improvements we can make already. One is try to do things faster. And another thing is try to at least have a sense of how big is the error. Let's see if there's other comments in here. Yeah, so and this is another way to say it. You need a large number of samples for accuracy. How big the error is will depend on the number of samples. If you have more samples, you'll get better accuracy, and understanding that trade-off will help us figure things out. So this the fact that it's random on its own is not terrible. If we can understand how big the error is and control it by doing more or less samples, that will really help fix this problem. So right now, as written, it's pretty terrible, but by fixing it and at least knowing how big the error is, it's going to depend on the number of samples. Depend on number of samples. That will really go a long way to like reducing this problem. Like we'll still have error, but at least we'll know it's definitely more than 0.4 or whatever, Okay, let's see. Yeah, if the input is bad, the Monte Carlo can be bad. But that's true for any algorithm, right? Like if you don't have the right, if the input is bad, it's going to be bad no matter what. Yeah, so I think you guys are identifying the 2 major things, speed and accuracy. And there are really good ways to improve both of them. That's the next thing we're going to do. So before we jump into the non-Monte Carlo way, we're going to improve our Monte Carlo. So two important improvements to be made. One is do things in parallel. And this is speed up. And the other thing is understand error. Okay, and it's going to turn out that the more samples you have, the smaller your error is. And so if you're speeding things up, that essentially means you can run more samples in the same amount of time. So speeding things up is actually, in a way, equivalent to reducing the error, assuming you have a fixed amount of time that you want to wait. So understand the error. This is depends on number of samples. So more samples leads to less error. And that's another reason why speeding it up is so important. We want to speed it up so we can run even more samples. Okay, so we're going to do this one first, understanding the error. And this is where it was important that you had taken a basic stats class or like a probability class. There are some theorems from the theory of probability from stats that tell you how big the error is. So the error We're going to understand it from stats class. Okay, which theorem? Does anyone know which theorem from stats class could help us with this error? You could type it in the chat, or you could put your hand up, or you could just yell it out, whatever you want to do. I'll let you guys think for a sec. Which theorem from stats class tells you about the size of the error? Maybe I'll start giving some hints. This is the thing we want. The thing we want is the expected value of the reward given x0 equals x. What do we have?
Is it the central limit theorem?
Yeah, it's going to be the central limit theorem. Very good. So it's going to be the central limit theorem. We want to know this expected value. What do we actually have? We don't have an expected value. What we have is a sum of random variables. So we have the sum from I equals 1 to reward, maybe to number of samples. Number of samples. And we have the rewards, the reward after sample I. And then we divided it by the number of samples. That's what our code is doing, right? It's adding up the total reward, that's this thing on top, and we're dividing it by the number of samples. And this thing is a sum of n sample independent random variables. So by the central limit theorem, the central limit theorem says that this thing is equal to, this is by the CLT. Okay, the CLT doesn't actually say things are equal, it says they're equal in the limit. So let me write it like this. The CLT says it is in quotes equal to, what is it equal to? It's equal to the expected value. That's what we want. Plus some normal random variable. Let's just do normal like this. So, okay, I'm gonna write it like this. It's 1 over n to some power, n sample to some power. So I'm gonna call the power, it's a special power, let's call it alpha. Special power alpha. And there's also the mean and the variance, of the normal distribution, mu and sigma. So the most important things you need to know about the central limit theorem is what is the power alpha? The power alpha tells you how does the size of the error, this normal distribution is basically the size of the error, how does it shrink as you increase the sample? So alpha is the power of the sample size. Now maybe power 4, scaling power of the sample size. Mu and sigma are the mean and variance. Mean of normal, variance of normal. Okay, and if you took a good stats class and you understood the central limit theorem, like, well, all of this stuff is like, these are the 3 fundamental things of the central limit theorem. So hopefully you took a good class where they made a big deal out of what these things are, and not just like looking things up in tables. I'll say one more thing. The equals in quotes is in the limit. So in the limit, n samples goes to infinity. The limit of the left-hand side is equal to the right-hand side, or the difference between them is the limit is 0. So that's what equals means. Of course, they're not exactly equal for any finite n sample. They're equal in the limit. It's the central limit theorem. So what are they? Alpha is a half. And so what this means is that really things are shrinking by 1 over n sample. So if you double the number of samples, that doesn't decrease the error by a half. It decreases it by 1 over square root of 2. So the error is proportional to 1 over n sample. Mu, the mean of the normal, is 0. These are the answers. Mu is 0. Why is mu 0? Because I already took out this term here, right? So we're trying to estimate something. The thing we're trying to estimate is the mean of the thing plus some noise. The noise is mean 0. It's centered around what we're actually trying to estimate. Okay, so that's good. In other versions of the central limit theorem, people won't write this term that I have in blue, and they'll put the mu there. So that's why it's good to know that. And lastly, sigma is the variance of the rewards. So that's another thing you have to know. If you don't know the variance of the rewards, here I'm just adding them up. If you don't know the variance of the rewards, you don't know the variance of this normal distribution. So without this ingredient, you cannot estimate the error. So the first thing to improve to understand the sample, the error, we're going to use this. There's going to be one ingredient, and the other ingredient is we are going to figure out what is the variance. We're going to find or estimate the variance, find the variance, and then we're going to use 1 over square root of n samples to find error estimate. Okay, and how do you find the variance? Well, the variance of some random variable x is the expected value of x squared minus the expected value of x squared. So when you run your Monte Carlo simulation, if you are only trying to figure out the expected value of x, you will never be able to accurately measure the size of the error. And so the secret is, while you are running the simulations to do the expected value of x, at the same time, also keep track of the expected value of x squared. So you should never ever do a simulation where you only do the expected value. You should always do the expected value and the expected value squared, and that way you can use the you can calculate the variance, or at least estimate the variance, and then you're on your way to using the central limit theorem. So estimate this. Okay, so this is the first improvement we're going to make to our code, and that is like the next block down. Is we are going to do the same thing, but we're going to do it with variance. So exact same method, Monte Carlo method. The core idea hasn't changed, but we're going to try to figure out what the error is by keeping track of the variance and using the central limit theorem. So we are going to estimate the variance, and then we're going to use the central limit theorem, and variance estimate to get error bars, to estimate the error bars. So this should remind you of stats class. Okay, so same thing as before, same exact situation as before, but instead of just keeping track of the total rewards, which would give me this like random variable expected value, I'm also doing the total rewards squared. So the code is exactly the same kind of thing, but instead of just adding on 1, I add on to the total rewards, I add on 1 squared every time there is a reward of 1. And this is a little silly because in this case, the reward is only ever 1 or 0. And 1 and 0 have the property that 1 squared equals 1 and 0 squared equals 0. So for this particular special example, the total rewards and the total rewards squared are exactly the same. Okay, it occurs to me, I shouldn't say the total rewards squared. It should be the total squared rewards, right? We're adding up, we're doing the sum of the rewards squared. In this case, they're exactly the same, but in general, they'll be different. So it's really important to keep track of this. Finally, we estimate the expected value. That's the same as before, the total rewards divided by the number of samples. And then I'm estimating the variance by using the formula, this formula. So we estimate the expected value of x squared. That's this reward squared term. I divide it by the number of samples, and then I subtract off the estimate. And this gives me 2 numbers, the expected value and the variance, and I return both of them. So this function returns both the expected value estimate and the variance estimate. And using that and the central limit theorem, we can make a confidence interval. So Gaussian random variable of mean 0 and variance 1 is within -2 to +2 95% of the time. And therefore, expected value, okay, this therefore is maybe you need to make some assumptions about how probabilities work and frequentist versus Bayesian and all that. But, essentially speaking, the expected value of something that you want to do is within the empirical average, the sum from I equals 1 to n samples of the rewards I divided by the number of samples minus 2 times the variance divided by the square root of the number of samples. Okay, maybe let's rewrite this like this so there's less notation. So a normal distribution is within -2 and +2 95% of the time. By the central limit theorem, you want to compute some estimate for the expected value of some number that is within the empirical estimate. I'm going to call that x expected value of x hat. That's the empirical estimate minus 2 times the empirical variance divided by the square root of the number of samples. 2. So that's one end of the interval all the way up to +2 times that. So from -2 times that to +2 times that is a 95% confidence interval. Okay, so if you believe the central limit theorem and you believe this fact from basic stats, that's how we compute things. And that's exactly what we do here. So we take the variance estimate and the expected value estimate from the last function we wrote. So nothing different here. And we just output this interval. And the interval consists exactly of what I said. It's what you estimated the mean to be, plus and minus twice the variance estimate divided by the number of samples with a square root. And the square root comes from that alpha equals 1/2 from the central limit theorem. So all of this is, maybe I should say, 2 sigma confidence interval by the central limit theorem. Okay. So if I run it, okay, I think I got to run this to do the simulations. Now, instead of just outputting a single number, now I have a whole interval, and I'm 95% sure that the real answer is somewhere in the interval. If I run it exactly the same thing again, 10 to 5, let's do only 100 samples like we did before. So now I'm 95% sure the real answer is between 0.36 and 0.56. And that really shows you that before, when we were running it, we were pretty, we thought it was somewhere around 1/2, but we're not 100% sure where it is. And if you increase the number of samples, you get a tighter confidence interval. If I increase it by a factor of 100, so I add 2 zeros, that should shrink it down by a factor of 10, right? If you increase the number of samples by 100 because of this square root thing, the confidence interval should shrink by a factor of 10. Right now, the confidence interval is like a size 0.2, right? The width of the interval is like 0.2. So if I shrink it by 10, it should be like 0.02. So we should at least have the first decimal right. Let's see what happens when I run it that way. So between 0.484 and 0.505. Maybe I can spoil. You can probably guess what the real answer is going to be just based on this picture. Where was the picture of the man? Is the man here somewhere?
It's up a bit.
Yeah, here we go. This is the one. So we're doing this one with 10 and 5. You can probably guess what is the probability that the man reaches the house before he reaches the skull and crossbones. It's 50%. He's exactly in the middle. They're symmetric. So we should be getting 50% here. And you can see that our confidence interval says it's between 0.484 and 0.505. So we're getting very close. If you increase it even more, who can guess what's going to happen when I increase it by another factor of 100? Nothing happens because now it takes too long to run. So the next thing we got to do is figure out how to make it faster. And next class, we're going to do this thing in parallel. And overall, we're going to get a 40 times improvement in the speed. So it's going to run 40 times faster by the time we're finished. That is going to be maybe the key programming idea of this course is never ever use for loops unless you absolutely have to. For loops and while loops and this kind of thing, they are very slow because they only do one thing at a time. You really want to be doing as many things as you can at once. And you want to use these built-in functions in Python that do everything in vectors. Because really those are the workhorse of doing everything at once on like modern computer processors. Okay, here, it ran, it finished, and we got between 0.498 and 0.5003. So the right answer is in that interval somewhere. We have a really good idea of not only what the answer is, but how close we are. Okay, so what did we do today? We did the first check mark, or the first thing to improve. We are understanding the error. We've done that, hopefully. So if you need to review your central limit theorem, and tomorrow, we are going to do things in parallel and speed things up. And then we're going to learn a whole different way to do it as well. But that's it for today's class. On Wednesday, we'll start to do things in parallel. make sure that you think about who you want to work with for the project. So partner and preferences, you can submit that form. Okay, it's 12:20. I'll stick around for questions and so on, but that's it for today.
Hey, yeah, I was just wondering. So on Friday, you said we had all this stuff to do, questions 1 and 2. Do we have the stuff
Yep.
to do question 3 now, or is there still more stuff to learn?
So for question 3, the only thing you need to know is how to set it up to be a reward system.
Okay.
So question 3 is asking you for the expected amount of time until something happens. And to do that, you need to be able to set up the expected amount of time as a reward system.
Okay.
That part we haven't done yet. And also how to solve it, we haven't done yet, right? Like we're getting to that. But the part of question 3 that you can totally do is take the problem and write it as a Markov chain. And I think that is like 80% of the work of that problem. And that part you can do.
Cool. And the stuff we did today, is that stuff in the same textbook section that we were doing like last week?
Okay. So this stuff about Monte Carlo is not in the textbook at all. So the textbook is all like theory. There's a little bit about it in the other textbook, the reinforcement learning textbook, but it is in a more complicated way. So yeah, for now, this is just like the basics of Monte Carlo, which we had to get to at some point, and we'll do it when we do it again fancy, when we do the not only the optimal value, but also the optimal value and decision or action. We're going to kind of do more Monte Carlo there, and there'll be a reference from the other book. Yeah, I can try to dig up a reference for you guys as well.
Cool. Thanks.
Yeah, no, great question, Harry. Thanks.
I have a question about the midterm project.
Yeah.
So problem 1, we have a state space that's from 0 to end state -1. So
Right.
is end state just something, can it be just a user input?
Right. So I think in the program, and you should definitely check the template, which has the input for the program, you just input the matrix. And you can assume that the matrix is a square matrix. And if you want to get end state, you should do like the size of the matrix.
Okay.
So I think, yeah, the command that you could use is numpy.shape of matrix. And that'll give you it'll say like 10 by 10, and then you'll know the answer is 10. So if you really want the number, you could do like the numpy.shape of the matrix, open square bracket, 0, close square bracket. That should give you the first entry.
Okay.
Yeah, that's a great point. I think you don't actually, in the way I wrote it, I never needed that. So you can, and this is part of doing it with like all the built-in vector functions. If you do it that way, it'll automatically do these kinds of things for you. So you can kind of find a way to do it that uses only the vector functions, and then you can skip like little things like this.
I had a question about number 1 as well.
Yeah, go ahead.
It's more just to clean up my code. You say a real value between 0 and 1, but if you use random uniform, you're not going to get a value of 1, correct?
Oh, sure. I mean, so if you take a random uniform between 0 and 1, for any fixed value, you never get that value.
Okay, I just want to make sure because I put a clause in case it was 1, but I can take care of that. Okay, and then I did have a question for 2 as well.
Yeah.
When you say the rainy day state on day n, do you mean the specific state where it is only rainy on day n and not previously, or do you mean any day that it has rained on day n?
Yeah, I just mean if I go outside on day n,
is it raining?
Do I need an umbrella
Perfect.
or not? Yeah.
Okay, thank you. That's all.
Yeah, that's great. Yeah, and I believe there was a small typo that Rob pointed out to me that on CampusWire, that apparently in question 1 I say given that it's sunny today, but that's not enough information. So you're supposed to be given that it's sunny today and yesterday. But I will double check that and fix that.
For problem 2, part C, where we have to find the exact value of the limit.
Yeah.
If we use like something like a while loop and just let n get really large, then that's not really the exact value, right? That's an approximation.
Yeah, that's right. Yeah.
Okay, cool. So that's probably not an option. So option 2 is I set up like a linear equation of the form ax equals b, where you have A is a matrix and B is some like solution vector. So, and then I tried to use Jack's NumPy's linear algebra solve function to solve that, but I just get not a number for all of the entries in the vector.
Yeah. So the problem with solving it is that like when you say solve, basically the computer is kind of computing the inverse matrix.
Right.
And the inverse matrix works when there's a unique solution. But do you remember in class we did it and we got a not unique solution, right? It was
Yeah,
like we were solving for A and B and there's no unique solution. So we needed this extra bit of information, and you got to figure out how to like incorporate that.
Okay.
Yeah.
Right.
I will say in problem 2, it's also like a specific problem. Like you don't need to make your code super duper general. So if you can like, you know, you can it's okay. It doesn't need to be like as like for example, in problem C, you're gonna have some matrix, and that matrix has a particular set of eigenvalues. Like it's okay to look at the eigenvalues and be like, I'm gonna turn off these ones or whatever you do. It doesn't need to run in general.
Okay.
Yeah, but you're definitely on the right track. Yeah. Any other questions or comments about anything? Okay. Well, if not,
we were going to talk after class, right?
yeah. So me and Matt are gonna meet and talk for a bit. But otherwise, see you guys next time.